Hello everyone, my name is Leonardo and today I'll present our work Structural Adapters in Pretrained Language Models for AMR-to-Text Generation. This is a joint work with Yui Zhang and Irina Gurevich. So in this work we are interested on AMRs. AMR stands for Abstract Meaning Representation, and it is a semantic formalism that represents the meaning of a sentence. So here you can see a AMR and a sentence that describes the meaning of this AMR. Our task is AMR-to-Text Generation, and this task, the goal of this task is producing a text which verbalizes the meaning encoded by the AMR graph. And usually for this task, we use graph-to-seq or graph-to-text models, where the AMR is the input and you generate the text. However, this is a challenging task because it's difficult to properly capture the complex structural information of this input graph when we fine-tune a pre-trained language model for this task. So previous work proposed to linearize those graphs. So the idea is that you use some algorithm like DFS to traverse the graph, and you generate a sequence of edges and nodes, and you use this linearized graph together with the sentence. So you have this pair and you use these pairs to fine-tune those pre-trained language models. However, when we linearize graphs, we lose some important information. So for example, the graph structure is not directly exploited. This is because the linearized representation weakens the structural information. So how to properly encode the graph in pre-trained language models is a challenging task. So previous work in AMR-to-Text Generation without pre-training used graph encoders instead of sequential encoders to encode the structure of the graph. That is, which nodes are connected with each other. However, pre-trained language models, they are pre-trained on natural language. And linearized graph structures are different from natural language. And intuitively, knowledge from large-scale pre-training cannot be fully transferred when you use structured data such as graphs or linearized graphs. So how can we explicitly encode the graph connectivity into a pre-trained language model? So this is the main question of this work. So we propose an adapter model that encodes the graph structure into the pre-trained language model during pre-training. And the idea is to explicitly model the input graph structure. So in a nutshell, adapters are sublayers that you add in each of the layers of a pre-trained language model in both the encoder and decoder of a pre-trained language model. And in our case, we add this adapter sublayer after the feed-forward sublayer of an encoder layer, and also after the feed-forward sublayer of the decoder layer of a pre-trained language model. And after we do that, we will train the adapter weights or the adapter parameters, while we freeze the parameters of the pre-trained language model, the other parameters. However, vanilla adapters from previous work, they do not model the graph connectivity. So this is an illustration of a vanilla adapter from previous work, where we have a layer norm, after that we have a feed-forward layer, after nonlinearity, and another feed-forward layer. And you also have a residual connection here. Finally, the self-attention mechanism of the encoder of pre-trained language models treat the sequence of nodes as a fully connected graph, greatly diluting the graph structure of the input graph. So in this work, we proposed a new adapter model called the StructAdapt, where we encode the graph connectivity utilizing an augmented adapter model. And for that, we use a graph convolution in order to learn node representations based on message passing between nodes in the graph. And the idea is that the graph structure will be substantially impacted by the node representations. So here we have an illustration of StructAdapt, where you add a graph convolution that will encode the relations between nodes in the input graph. So the StructAdapt will be used in each encoder layer of the pre-trained language model, and a adapter will be used in each decoder layer of the pre-trained language model. One important issue when we are working with pre-trained language models is that they use vocabulary with subword units. However, it's changing how to represent graphs using subword tokens. So in this work, we construct subword graphs. So we do the following. So first, given a AMR structure, we generate nodes from the heads, and after the tokenization, if a token, each token of a node is connected with the corresponding node that this node was connected. So in this case here, Go1 was split in different tokens, and all of these tokens are connected with arg1. So our structure adapter is a two-layer architecture. First, we have a graph convolution that will generate a representation of the node V based on the representation of node V and the representations of the neighbors of the node V in the input graph. And after, you will have a feed-forward layer that will be calculated based on the representation of node V. And in our work, we consider two graph neural networks as graph convolutions. The first one is graph convolutional networks, and the second one is relational graph convolutional networks. And the second one important thing is that it models the direct and reverse relations between two nodes, that as it was shown that it benefits encoding graphs in NLP. So our models were initialized with Pretrained T5. We evaluate with different metrics. We also use MF score that measures how well the source AMR can be reconstructed from the generated sentence. And finally, we execute human evaluation. So in our experiments, we evaluate with both T5 base and T5 large, and we compare against fine-tuning, and only fine-tuning the top two layers of the encoder and decoder, and only fine-tuning the bottom two layers of the encoder and the decoder, and with the vanilla adapter, that is the adapter without any graph convolution. So first note that fine-tuning the bottom layers performs better than the fine-tuning the upper layers, and it suggests that the lower layers have significant impact in adapting the pre-trained language model to structured data. Also note that training only around 7% of the parameters using adapters improves over fine-tuning. Also, structured adapter using graph convolutional network trains only around 2% of parameters, and it improves over fine-tuning and also over adapter, even using much less parameters. And also, structure adapter with RGCN is better than structure adapter with GCNs using less parameters. So this shows that encoding the reverse edge directions is very important for this test. The results for the other dataset, LDC 2020, follow similar trends, and you can see the details in the paper. We also execute a human evaluation using Amazon Mechanical Turk, where we measure the meaning similarity, that is, how close in meaning is the generated sentence to the reference sentence. And here you can see that the gains from structure adapter mainly come from the large graphs. So this suggests that structure adapter better encodes larger graphs. In this experiment, we investigate the number of parameters in the adapter approach. First, note that structure adapt is consistently better than the adapt approach. And structure adapt, training only around 1% of the parameters, achieves similar performance than the adapt approach, training almost 9% of the parameters. And this demonstrates the effectiveness of injecting the graph structure into the pre-trained language model. Here we investigate how the amount of data for training impacts in the performance. First, note that the adapter-based approach improves over fine-tuning in the low data setting. The gap between adapt and fine-tuning decreases when the training size increases. Finally, structure adapter outperforms adapt by around 5 blue points on average, demonstrating again that it's beneficial for AMR-to-Text Generation, properly encoding the graph, the input graph. Here we have a case study where we have a AMR graph, we have the reference sentence, and we have examples of generated sentence from fine-tuning and structure adapt approach, training with the whole data or with only 2000 examples. So you can see that fine-tuning fails in generating a sentence with the correct concept breakup, and overall structure adapter produces a more accurate text, generating correct pronouns and mentions. So a critical advantage of modeling the graph structure is to be less dependent on linearization strategies. In this experiment, we evaluate how the models behave when we change the way that we linearize the graph. So in this example, you can see two graphs that has the same meaning but have different graph structures. And we investigate with three different linearizations: canonical, the original human-created order for the AMR; reconf, where the human-generated order is ignored; and random, where we select at random a node in the graph and start the linearization from this node. So here are the results using blue score. And note that both reconf and random has a negative impact in the performance of all models. However, StructAdapt is less impacted by different graph linearizations. In particular, for the random linearization, StructAdapt has a much better performance than previous approaches. This shows that StructAdapt is less impacted by different graph linearizations. We also evaluate the models based on the graph properties. In particular, we investigate three different graph properties: graph size, graph diameter, and reentrances. Reentrances are nodes with more than one entering edge. So first, note that StructAdapt is better to encode complex graphs where you have more than 60 nodes, and graphs with a diameter larger than 20. And also note that StructAdapt has the better performance when you have more reentrances. So this slide concludes and summarizes my presentation. In this work, we propose StructAdapt, a adapter architecture that explicitly models the graph structures into pre-trained language models. We showed that our model is more effective when encoding complex graphs and is robust to different graph linearizations. In this link, you can find the StructAdapt code. Thank you very much.